Hello audience. Today we will discuss about the charge pump circuit, getting higher voltage from a low voltage source. Boost converters are inefficient at low powers, since a lot of energy is consumed just for keeping the regulation on point and driving the power switch. In addition, switch mode converters of this type are noisy. This is a problem if you are dealing with sensitive circuitry. The answer to this problem is the charge pump, which by itself is a kind of switch mode power supply. As the name suggests, this kind of converter moves discrete charges around, and the component that stores these discrete charges is the capacitor, so this kind of converter is also called the flying capacitor converter. A charge pump creates discrete multiples of the input voltage using capacitors. Basics of charge pump. The basic charge pump circuit is a switch mode DC to DC converter that is often needed in designs requiring more than one DC supply voltage. It is made up of switches and capacitors. The switches are usually diodes in discrete designs, but are also MOSFETs in IC versions. The capacitors are electrolytic or ceramics depending on the switching speed. There is no need for an inductor. All charge pumps are some mix of switches and capacitors. Most integrated charge pumps use MOSFET switches with a low on resistance and an integrated clock. The capacitors are always external to the IC so that the type and size may be selected according to the clock speed and the ripple requirements. The circuit may or may not be regulated. In practical designs using discrete components, Schottky diodes are usually used instead of conventional diodes because of their lower forward voltage drop. However, IC-based charge pumps do not use diodes. Instead, they use MOSFET switches with low on resistance RDS, on. Charge pump efficiency is high, in the range of 90 to 95%. Switching regulator emissions. Conducted emissions ride on the wires and traces that connect up to a product. Since the noise is localized to a specific terminal or connector in the design, compliance with conducted emission requirements can often be assured relatively early in the development process with a good layout or filter design. Radiated emissions are a different matter altogether. Everything on the board that carries current radiates an electromagnetic field. Every trace on the board is an antenna and every copper plane is a resonator. Anything, other than a pure sine wave or DC voltage, generates noise all over the signal spectrum. Even with careful design, a power supply designer never really knows how bad the radiated emissions are going to be until the system is tested. Filters are often used to reduce EMI by attenuating the strength at a certain frequency or over a range of frequencies. A portion of this energy that travels through space, radiated, is attenuated by adding metallic and magnetic shields. The part that rides on PCB traces, conducted, is tamed by adding ferrite beads and other filters. EMI cannot be eliminated but can be attenuated to a level that is acceptable by other communication, signal processing and digital components. Moreover, several regulatory bodies enforce standards to ensure compliance in both industrial and automotive systems. Modern input filter components in surface mount technology have better performance than through-hole parts. The low minimum on and off times required at higher operating frequencies result in higher harmonic content due to the faster switch transitions, thereby increasing radiated noise. However, these high switch edge rates are needed to get higher conversion efficiencies. A switched capacitor charge pump does not exhibit this behavior since it operates at much lower switching frequencies and most importantly can tolerate slower switching transitions without degradation in efficiency. An alternative solution to EMI issues. The tried and true solution to EMI issues is to use a shielding box for the complete circuit, and even then, a shield does not prevent coupling to sensitive circuits inside the box. Of course, this adds cost, increases required board space, makes thermal management and testing more difficult and introduces additional assembly expense. Another frequently used method is to slow down the switching edges. This has the undesired effect of reducing the efficiency, increasing minimum on, off times, and their associated dead times, and compromises the potential current control loop speed. Thanking you.